Hello, I'm Ken Keller from the Office of Nuclear Energy, here to talk about a grant opportunity titled Maintaining and Building Upon the Halden Legacy. And oh, close a little me, it's covering my text, little screen. All right. Okay, I'm the federal point of contact, Ken Keller. My technical point of contact out of Idaho National Laboratory is Colby Jensen. This grant is offered for universities only for an expected 3-year term and up to $400,000. You may have heard the Halden reactor is no longer going to be available, and with that, there's two things we're losing: irradiation volume, irradiation capacity. But that turns out to not be the big deal. We are exploring other reactors, for example, the MIT reactor, the Advanced Test Reactor in Idaho, and the high flux isotope reactor, as well as several European reactors. What is of concern to us in the Office of Nuclear Energy is the loss of their incredible experimental and diagnostic capability. In this photograph to the right, you'll see several forms of diagnostics. Most of them are LVDT-based, linear voltage differential transformer, where the parameter you're trying to measure somehow gets translated into a physical displacement of basically a transformer core, and a signal comes out. But Halden's expertise in diagnostics goes well beyond that. So with loss of the access to the Halden reactor, we're at risk of losing these diagnostics. Now, one good news we've heard is the staff of Halden is been reportedly, none of them will lose their jobs, but they're losing the main facility that drives their work. So at least for some indefinite period of time, hopefully on the scale of years, we will have those brilliant scientists and engineers and technicians available to work with. One area of interest that we're looking at from a recent conference is the eye holes at the Advanced Test Reactor. Those are holes out in the periphery of the reactor that have a flux comparable to the Halden reactor, where Idaho National Laboratory will be looking at developing loops. Now, these could be the full-up test loops that are in the central part of the core. Those are very complex systems with complex support systems. But there's also the possibility of incorporating the Oak Ridge National Laboratory created thermosiphon. It's a thermosiphon is a more simple device. It's used to use the two-phase flow to maintain the temperature of your choice. So the main things we're looking for in this call are diagnostics. But in addition to diagnostics, Halden has great experience in rebuild capability, in taking, for example, a full-up commercial fuel rod and converting it to an instrumented experiment. That's also a skill that we would like to see. Also, Halden occasionally, in mid-experiment, would recalibrate or swap out diagnostics that are shorter-lived. That's something I don't think we do too much. In America, we will swap out flux collars, an example, to get depleted, but we don't do too much of diagnostic swap out. So that's another area we're interested in. So to be more specific, in this call, here are some of the real-time in-core diagnostics that we're interested in seeing. But this is just an example list. Definitely the diagnostic you propose needs to be relevant to our programs on our interests. But here's some of the things that we're interested in. Creep measurements, crack propagation measurements, measuring swelling, corrosion or crud buildup on the cladding, obviously temperature and pressure, flux levels, monitoring two-phase flow, fission product transport, and also research that enables in-core application and associated logistics is also encouraged, such as focuses on miniaturization, non-contact or non-intrusive, as well as innovative data transmission techniques, such as wireless methods. This is also encouraged. Halden, everything that Halden has pretty much has a wire or a pipe coming out of it. We're open to, that's a real annoyance for an experimenter. So if we can avoid those wires and cables and pipes, that would be great. Here on this picture is an example of Halden's creativity. This is a crack growth test rig that goes in a reactor. At the bottom, you'll see a bellows that can be pressurized externally. The bellows is like the hands on a scissor or pair of pliers. And what happens is the experimenters can control the force pulling a cracked sample apart. And then you run electrical current through it or have a voltage, and the current is proportional to the crack size. So real time, you can apply a known force and measure the response. That's another example of Halden's brilliance. So I mentioned earlier, emphasis is going to be awarded on diagnostics that can directly benefit areas of interest in the Office of Nuclear Energy. So I encourage you to get up to speed on those things that we're currently working on and see if you can help us improve the measurements. And especially, we're especially interested in in situ diagnostics that we can't reconstruct during post-irradiation examination. For example, crack growth rates. Okay, you can see a crack at the beginning of your experiment, then take a sample out and measure the crack, but you don't know the growth rates. You don't know if it's linear, nonlinear. What was there a certain flux level or amount of radiation damage where the thing really took off or really slowed down? And so if there's any kind of nonlinear phenomena, we would love to measure it real time. And this final graphic I have here is a graphic demonstration of the rebuild capability that Halden had. The left figure is a full-up fuel assembly. They cut that down and make a shorter fuel rod segment, and then they instrument it. You can see here they drilled down through the fuel and put in a thermocouple, and at the bottom they put in some type of bellows and LVDT to measure something, for example, the fuel stack growth, or perhaps the cladding growth. And there's some real magic in doing this, especially imagine if you have irradiated uranium oxide fuel that's already cracked, and now you want to drill a hole in it and put something in it. One technique is to use frozen CO2. Infuse CO2, high pressure, becomes liquid, freeze it, and solidify everything in place. Do your mechanical work, and then slowly thaw it out so you can retain the delicate structures of the fuel. So that's that's our here's our points of contact. Colby Jensen, I would direct you to for your technical questions. He's in touch with ongoing Idaho diagnostics development, so he can guide you as to what would be duplicative of what we're doing at the labs, and can help give you feedback. So with that, I will take questions.
We do have Colby Jensen on the line as well. Colby, can you hear us?
Yes, I can. Thank you.
Okay, we will take questions over the next few minutes. Please submit those questions, and we'll have either Ken or Colby answer them for you.
And Colby, feel free to chime in if you think there's critical things or pointers that I left out.
Well, thank you, Ken. I think you did a great job of highlighting not only the sensors, but the overall technology, the logistics that are involved with getting measurements out of the reactor, and the approach to irradiation that enables the data. So thank you.
We'll stay here for about a minute longer. If you do have questions, please type them up and submit them now. What is the expected TRL for a final project deliverable?
Because this is a grant to the university and there's a long term, it can be a fairly low TRL. You can stick your neck out and be creative on this with something that is unproven. In the interim, the national laboratories are going to be working more real time to more just directly reproduce the Halden capability, without being too creative. shamelessly just copying what the brilliant people have done. So feel free to be creative.
Is Halden involved at this time?
Yes, we just out in Idaho had a conference to assess the impact of the loss of Halden and to brainstorm solutions. And the Halden managers and tech staff were out at Idaho with a multinational lab and multinational group of, I think it was about 30, 40 people. And Halden very openly communicated their status, their techniques. They communicated they're very open in sharing their legacy. So yes, and there's every plan to continue involving Halden. I can't commit. I don't know what's been funded yet. Oh, okay. And Frank Goldner reminded me that on the Idaho National Laboratory website, there's a draft report published from this meeting, and it's worth looking at because it's a really comprehensive overview of all the facilities that could in the world that we think could replace Halden, and also a discussion of some of the technologies. The final report, it's out for comment now. So in early December, the final report will be available, and that should be a valuable resource and required reading for anyone who wants to submit an application.
Are you interested in data processing as well?
Yes, but I'd like to, I put a low emphasis on that because the challenge is putting stuff in the hostile reactor environment and getting data out. So I wouldn't say don't submit that, but you'd be at odds competing against rad hard technologies. That's really what we need to get, is get the signal out of the reactor. That's what this focuses on.
Is a final project deliverable expected to be a trade or feasibility study or some level of prototype development?
With this amount of money, I would expect physical work, some kind of prototype development. But if you're proposing something incredibly complex, then perhaps maybe it should just stay on paper and be feasible. But if someone is offering up hardware, testable, bangable hardware, that would be the preferable product. Colby, jump in if you'd like to put your.
I think everything you've been saying is I agree with, and I think you've said very well. The idea is, again, trying to be creative and open in terms of different ways that we could accomplish the goals that we have for getting data out of the reactor. Just that a lot of those issues are not, I mean, there's a lot of sensors out there that do a lot of great measurements that we cannot use inside of a reactor, whether or not it's the irradiation environment or it's the logistics that are involved or a combination. I think those are some of the key things to think about, is what has made Halden so successful for such a long time.
Colby just reminded me one thing I was going to mention in my presentation. One other attribute of Halden is the ability to put multiple diagnostics in one experiment. We were talking to an entity that was going to emulate some of the Halden tests, and they couldn't do all of them in one sample. They'd have to measure one thing in one of their samples and then move up the chain and measure one thing in another sample. So that's another attribute, is jamming in as many diagnostics as you can into to one, say, fuel rodlet.
Okay, I think those are all the questions we have. Thanks, Ken. Thanks, Kobe, for being on the line.